You're welcome again. And today we're looking at circular and simple harmonic motion. I remain Mr. Jude Anadozie, and I'm privileged to take these subjects and to share knowledge, what I know on this. Circular and simple harmonic motion. First of all, I think we have to know what's a circular motion. We'll start with circular motion before we move to simple harmonic motion. So circular motion is defined as the motion of an object around a circle or circular path. Let's assume this is a perfect circle. The motion of an object around a circle or a circular path is known as what? Circular motion. So an object is said to undergo uniform circular motion when it is moving along a circular path. What? At what? Constant what? At constant speed. Okay. Sorry. I want it to be as simple as possible and also very easy for you all, for we all to understand. If this is the center of our circle and this maybe a string I'm rolling around from, I tie the string to a stone or to any hard object and I'm swinging it around. It's going like this, going circular. So let's assume that so as it's swinging around, one thing happens. It moves from this point to this point, right? In a circular path. Move from this point to this point. If you don't understand, what did I mean? Well, I mean that as the body is going around, let's assume it's my finger now going around the circle. As it is going around the circle, I have an object here. Okay, this is string, and this string is tied to this. Let's assume as you add there, you are watching it's going around the circle this way. Someone who is above, directly above my hand, what the person will see an object moving in a circle. Someone who is far from me, just the same eye level with this object going around, we see an object moving from left to right. You get me? So this object oscillating, initially is at this point. Let's call here this maximum displacement. Maximum displacement from the equilibrium position is known as what? Amplitude. It's known as what? Amplitude. This string can be displaced to this. This is the maximum it can go. So this is amplitude. So it can go to this point. This is not amplitude. It can stop here. It can stop here. It can stop here. No problem. But once it gets to this point, it can't exceed here because this is the maximum this string can go. So this maximum displacement can go from the mean position is known as what? Amplitude. Still on that, I'm trying not to enter simple harmonic motion. Let me limit myself to circular motion for now. So what do you observe here? At a point, this body moves from here to here. Then here forms part of a circle known as arc. Let's present this arc by what? Letter S. Now it move by what? Theta, displayed by theta. You already know your linear velocity. Linear velocity is what? Linear velocity. Let's present this amplitude is taken as the radius. Are you getting me? Linear velocity is same as what? Displacement over what? Time. That means displaced from this point to this point with respect to time. At time 0, it was here. At time t, it was here. At that time that it was here, the displacement is what? S. It has been displaced. Now, what else do we observe? Discover that this theta, what, okay, what determines this displacement here? Are you with me? How many displacement here is what? Theta. As theta increases, our S value will increase. As theta decreases, our S value will what? Decrease. And our radius remains what? Constant. The radius remains constant. So that means A is like proportional to what? Theta. So this being our constant, I can remove this, put equals to here, put what? R here. Now, take note. This body is moving around with constant speed, but at what? Uh, at constant speed, but our velocity changes. Why the velocity change? Velocity change as a result of what? There's always change in direction. At this point, this is direction. At this point, this is direction. At this point, if it's moving this way, this is direction. At this point, this is direction. There's change in what? Direction. And because change direction, we say what? Velocity is not velocity is not constant. You getting me? Velocity change, but speed remains constant. And I've said that velocity is displacement over time. And this guy changes. Are you getting me? Now, what else do we know? Since velocity is linear velocity v, linear on a straight path, it's change of s with time. So, what is now angular velocity? From the name angular velocity, omega, angular velocity, it was change of angle with time. Linear is change of displacement with time. Angular is change of angle with what? Time. Theta over what? Time. Trying to relate these two, so we'll get our equation of what? Circle. After deriving the equation of circle, I will pause. Later, I'll continue from there, so that the video will not be what? Too lengthy. So linear velocity is change of displacement over time. Angular velocity is change of angle with time. So, and the displacement is subject to what? Theta. And our R is what? Constant. So, using this to substitute this, will give us what? B equals R theta over time. What are we seeing here? We are seeing here R omega. Because this equals this, the equals that. This equals what? That. That's omega. So we'll be able to what? Derive this. We've been able to what? Derive that equation. So what should we do next? Next point of action. Okay. Okay. Let me erase this. Okay. So be able to derive that V equals what? Omega R. Omega what? R. And When you define acceleration, relating it to what? Simple harmonic motion. Acceleration, I don't want to go through the differentiation or integration, but when I start, when I enter fully in simple harmonic motion, I'll, I will go down to those differentiation and what? Integration. Omega square what? Omega square r. That's our section, that's our velocity. And what else again? What else again? You know that F equals to what? F equals to what? Mass times what? Acceleration. Mass times acceleration. And this is same as what? Mass multiplied by what? Omega square r. From here, I can say omega equals v over what? R. Correct? Making omega the subject or the formula, thereby dividing both sides by what? R. Divided by R, divided here by R, you get that formula. So using v over r to go in for what? Omega square will be what? M v over r all squared multiplied by what? R, which will give us force, our circular force on a circular body equals to what? Mv square over r square dot r. This r element one of this r gives us what? Mv square over r. So this is our circular force. And whenever a body is rotating at a point, two forces act on it. The first force is the force that pulls the body to the center, and that is what is that is also known as what? That is called centripetal force. Called centripetal force. And according to Newton's third law of motion, it says for every action there is equal and opposite reaction. So if there is a force that pulls it inside to the center, which equals this force, there should be another force for this body to be at equilibrium, not falling in. There should be another force pulling it what? Out from the center. And that force is known as what? Centrifugal force. Centri what? Fugal force. Centripetal pulls to the center, while centrifugal pulls away from the center. So what have we discussed today? From what we are seeing today, we've been able to get the relationship between linear velocity and angular velocity. That is the first thing I did. Then I brought a formula from simple harmonic motion. Acceleration proportional to what? Displacement. Are you getting me? So omega squared being our what? Constant. Then from here, I now what? Derive the force on what is circular body. Ma equals what? Mv square over what? R. Here now that means what? Our centripetal acceleration is v square over what? R. V is a linear velocity. Is A means acceleration, because this one is normally F equals to ma is linear force, and this A here is linear with acceleration. Are you getting me? So we'll have to get for the word circular, and from we have to know how to what the formula is being what derived. You need to know how the formula is being derived, And that is what I've broken down to you. I've broken it down to you for your own understanding. And if you have a challenge in any of the derivation, please let me know. You can go through the video again and again. So this is what we need for what? Uh, to calculate the force of an object moving around what? A point, or moving at a point, or moving in a circle. Knowing what? If you know the mass of the object, you know the velocity, you know the radius, can easily get the force. In a way, in the other case where you're not giving the velocity, just give the acceleration, you can go ahead and use this. What if you are giving the omega and the radius? You can still go ahead and use this. There is no issue. So from this point, we'll go into simple harmonic motion gradually. I explain what amplitude is. So I will build on that, bringing in frequency, period. From there, looking at the relationship between period and frequency. Then going through what? We've already derived this. This is when the body is moving what? At the what? At the maximum displacement amplitude. What if the body didn't get to the amplitude? It stopped at a point X. That will be explained in the next video also. And I'll give you the derivation of this. Yes, how can get this from by deriving differentiation and what, and integration. That is calculus. So just go through this video, watch it again and again, and if there's any challenge you have regarding circular motion, let me know. Or the next video I will drop will be what? Simple harmonic motion introduction. Thank you.